Hi everyone, thank you for tuning in to our tutorial on efficient dispersion-corrected hybrid DFT in FHI-aims. We will demonstrate how to run and analyze these types of simulations for two relevant use cases in both industry and academia. The first part will focus on crystal structure predictions for molecular crystals, while the second part will be about the properties of organic inorganic perovskites. FHI-aims is particularly well suited for these tasks because it can address large periodic structures, even up to 30,000 atoms, in an efficient manner using hybrid density functionals. This tutorial has been created in conjunction with the online webinar series. While you can complete the tutorial on its own, we recommend watching the talks by Dr. Volker Blum and Dr. Neumann first. Links to these talks are provided in the description. You can also find a full written version of this tutorial linked in the description with even more details and step-by-step instructions. To run the tutorial, you need a good understanding of the Unix command line, the FHI-aims code, and access to one or two nodes on the supercomputing center. We also recommend using the optional Python package CLIMS, which will save some time in setting up the simulations and analyzing the results. We've prepared the data analysis part with Python scripts, but feel free to write your own scripts or use other software if needed. For those new to Python in computational materials science, we recommend the MOSI tutorial, which is also linked down in the description. But don't worry if you're not a Python expert yet, we've prepared all the scripts in advance, so you can easily follow along. Now, enough with the introduction. Let's dive right into our first example on crystal structure predictions, starting with a quote from 1988. One of the continuing scandals in the physical sciences is that it remains in general impossible to predict the structure of even the simplest crystalline solids from a knowledge of their chemical composition. This is a quote from John Maddox in Nature from 1988. While significant progress has been made since then, crystal structure prediction remains an active and complex field of research. Accurate crystal structure predictions would allow us to computationally explore and engineer materials with desired properties before synthesis. This is particularly crucial for applications such as pharmaceuticals, where different crystal structures, also known as polymorphs, of the same molecule can have dramatically different properties, but are only separated by tiny energetic differences. The Cambridge Crystallographic Data Center has been instrumental in benchmarking current approaches through its series of crystal structure prediction blind tests, also known as the CSP blind test, which first started in 1999. These tests challenge international research groups worldwide to predict unpublished crystal structures only based on the chemical composition of the molecule. We will focus in this example on one specific part of blind test number 6, which was published in 2016, namely Target 22, and the publication by Hoya et al. In 2019, which not only used FHI-aims in their CSP workflow, but were also the best performing research group in that blind test. The general workflow for CSP consisted of two stages. A molecular structure is created based on the chemical formula. And then several crystal structure polymorphs are created and ranked in an approximate manner with force fields and cheaper methods. Details on this procedure can be found in the respective publications, but we will not go into more details in this part of the tutorial. We will instead focus on the second part, which is the accurate free energy ranking of the most promising candidates from the structure pool by dispersion-corrected density functional theory. In the interest of time and saving resources, we will only compute the rankings based on the two most promising candidates from the initial screening, namely structure N1 and structure N2. We of course have the unique advantage that we know that structure N2 is the experimentally observed crystal structure for target 22. Interestingly, structure N1 has been labeled as the most promising candidate after the first screening with cheaper methods. A common problem is that force fields and even certain DFT methods struggle to accurately represent the molecular geometry, particularly the hinge-like feature of the molecule. They often incorrectly predict a flat molecular conformation, however the actual stable structure, N2, correctly captures the non-planar nature of the molecule, with the molecules forming rows clustered together but offset from one another. We now want to verify this fact with some FHI-aims simulations. Let's start by creating a working folder and in it a geometries folder. The two structure folders can be obtained from the supplementary material of the publication by Volker et al. They represent geometries relaxed at the GGA level with the Tkatchenko-Scheffler dispersion correction and are given in CIF formats. If we want to convert these files to the geometry.in format for FHI-aims, we can use several tools such as GIMPs, ASE, Pymargin, and many more. Here we will use CLIMS. We can use the built-in CLIMS convert geometry command to convert both CIF files to geometry.in files with fractional coordinates. After running the command, you should now have two geometry files with 60 atoms each. As done in the original publication, we will compare the GGA functional PBE with the hybrid functional PBE0. In addition, we will compare several dispersion corrections, namely the effective pairwise Tkatchenko-Scheffler or TS correction, the inclusion of many-body dispersion interactions at the non-local level, MBD for short, and the exchange hole dipole moment model, XDM. We will use shortened acronyms throughout this tutorial to symbolize these different types of calculations. For example, a calculation with PBE and the TS correction is just denoted as PBE plus TS. The details for all these dispersion corrections can be found in their respective references and the FHI-aims menu. We here start on the PBE level and create the respective folders for the PBE plus TS, PBE plus MBD, and PBE plus XDM calculations. Copy in the geometry files we've just created into all the relevant subfolders. You should now have a folder structure which looks similar to this. Next, we create the control.in file for the PBE plus TS calculation. Here done for structure N1. We only need to specify a few keywords, which includes the PBE functional, the dispersion correction that we use, so in this case TS, as well as the K-grid. The K-grid that we are using is the same converged K-grid that was used in the original publication by Volker et al. Next, we attach the tight species defaults, again here with CLIMS. Keep in mind it's not necessary to use CLIMS for this part, but it saves us some time. The control.in files for structures N1 and N2 only differ in their K-grid due to their different lattice vectors, so please keep this in mind. Then we copy these control.in files to both the PBE plus MBD and PBE plus XDM folders. In them, you only need to adjust the dispersion correction keyword in the second line. For MBD, please change it to many-body dispersion NL. And for XDM, please change it to XDM tight. The extra parameter after the XDM keyword should be set to the same value as the species defaults that you are using. Now we can submit all 6 calculations and wait. This would take roughly 5 minutes per calculation when running with 64 cores. To analyze the results, we have prepared some Python scripts for you. The analyze energy script here reads in the different FHI-aims output files, which in our case are all named aims.out, and calculates the relative energies per molecule in units of kilojoule per mole. To run the script, you simply have to run the analyze energies.py script with the data folders as arguments, which we do here for the PBE plus TS plus MBD and plus XDM folders. After running, you should see 2 new files in your folder, an energies.md, so a markdown file, and an energydata.json file. We can already look at these results only with these files, but it's always helpful to also visualize these results. To visualize, we have also prepared a plotting script that uses matplotlib, plot energy data, which takes in the energy data.json file we have previously created. Please run the script next. You should now see a new energyrankings.png file, which you can directly inspect. You should see that all dispersion corrections incorrectly predict that the structure N1 is most stable. Even the more sophisticated MBD and XTM corrections have very similar relative stabilities of around 1 kJ per mole, while the TS correction predicts an almost twice as large gap. It's clear that the PBE functional in this case is not accurate enough, irrespective of the dispersion correction being used. Hoya et al. Have shown that the PBO0 functional, together with the MBD correction, performs the best for this blind test. Let's test and see if the PBE functional can correctly reproduce the experimental crystal structure for target 22 in our tutorial here. Let's start again by creating the respective folders, now for the PBO0 plus TS, plus MBD, and plus XTM calculations. We will make use of the restart functionality of FHI-aims in the following to save some computational resources. Let's start in the PBO0 plus TS folder and create the control.in file for structure N1. It now should be very similar to the PBE plus TS control.in file, but we change the exchange correlation line to PBE0, as well as add the LC restart write SCF converge keyword to write the restart information at the end of the SCF cycle. After creating the control.in file, we add the light species defaults as done by Hoya et al. To save some resources. More accurate results can be obtained with intermediate or tight species defaults, but the conclusions we present here remain unchanged. Then create also the control.in file for structure N2 by copying the file to that folder and changing the kgrid. Run now both calculations and wait until they are finished. Again, this should take you roughly 5 minutes with 64 cores. You should now see several restart files in each folder. These restart files are the density matrices stored for each of the 23 K points. Before restarting the calculations in this folder and to save some time, we will copy the output files except for the restart files to a new folder. Then we will adjust the control.in files in the PB0 plus TS folders to include the MBD correction. Here you only need to adjust 2 lines. The dispersion correction line to now include the many-body dispersion-nl keyword, as well as the LC restart keyword to now only read in the restart information. Restart now both calculations for structure N1 and N2. This should only take you around 1 minute. After finishing, please copy the output files to the PB0 plus MBD folder. Repeat the procedure for the XTM correction. Now, we only need to change the dispersion correction to XTM light. Remember, we use light species defaults now, so that's why we have to add the parameter light to the XTM keyword. Submit the calculations again, wait, and then copy the results to the PB0 plus XTM folder. Then, as the last step, we copy back the original PB0 plus TS results to the original folder. Now that all calculations are finished, we can finally analyze the results in the exact same manner as before. We have already seen there's no large difference between PBE plus MBD and PBE plus XTM calculations, so we will only include the PBE plus MBD results in the following. Run the analysis script for the PBE plus MBD, PBE0 plus TS, PB0 plus MBD, and PB0 plus XTM folders, and plot the results afterward. As you can see from the resulting plot, using PB0 plus MBD and PB0 plus XTM results in the correct stability ordering with structure N2 predicted to be the most stable crystal polymorph. The hybrid functional PB0 mitigates the self-interaction error and in doing so leads to a significantly better description of electrostatic and charge transfer effects. Interestingly, you can also see that PB0 plus TS still incorrectly predicts structure N1 to be more stable. It is thus necessary to combine the accuracy of hybrid functionals with the more sophisticated dispersion corrections like MBD or XXII. This is not only true for this specific target, but all the targets in blind test 6. Congratulations, you are now finished with the first part of this tutorial. We have seen that dispersion-corrected hybrid DFT can accurately predict the stability of molecular crystal polymorphs. For part 2, we will look at some organic-inorganic hybrid perovskites. See you then.